So this is example number 2 on vector calculus. So in this particular example, we have Nadine is trying to wash her car and she's using a nozzle. Okay, this particular nozzle, the problem says that this is equal to 0.42 inches, and the equivalent is 0.42 inches, and it's the same as 0.035 feet. Here the outlet diameter here is D is equal to 0.82 inches. And if I convert the inches into feet, you can show that that's equal to 0.052 feet. Okay, feet, sorry. The total length of the nozzle is 3.90 inches, or is equal to 0.325 feet. So we know that. And the problem also gives you the volume flow rate, and the volume flow rate is 0.841 gallons per minute. Or we can translate this into feet per second, just to have everything in the same units. The problem says steady, so steady is important. And what you're really asked for in this problem is, tell us what is the acceleration, tell us the magnitude of the acceleration of the particle across the center line, right? Across the center line. What is the acceleration? So to do this problem, we have to go back to the equations that we derived in the previous classes. And we derived that your speed, in general, in this case, is a function of x, y, z, and t. It's a function of u, I, plus v, j, plus w, k. And note that each one of these quantities also function x, y, z, and t in general, right? Now, A, we learned this, that's actually is the same as, it will be the same as your velocity times time velocity vector times time plus u partial of u respect to x plus v partial of v respect to y plus w partial of w respect to z. Okay, now note that this is 0 because the problem states that this is steady. Note that these two are 0 because we are working across the center line. Okay, the fluid is along the center line. And we moved our coordinate system such that my x falls along the nozzle line, the flow line. Okay, so basically in the problem, you're left with A is equal to u partial of u respect to x. This is approximately equal to u average, delta u, delta x. So it's going to, the average is what goes out, the outlet flow speed minus the inlet low speed divided by 2. This is a plus, I'm sorry. This is the average. And then this is nothing else than what goes out minus what got the speed that comes in divided by delta x. So your speed, then we can approximately say, is the same as what your speed that goes out minus the speed that goes in divided by 2 times delta x. So now in the problem, I need to find what my outlet and inlet speeds are. And we can do that by starting by the fact that I know my flow rate. Okay, my flow rate is given by 0.00187 feet cube over second. Then my inlet speed, I can basically divide this by my inlet area, and that would give me 0.00187 feet cube over second divided by pi 0.035 squared feet squared. Note that I used the conversion in feet. Okay, so that gives me a value of 1.95 feet per second. Now I can do the same thing for the outlet. The outlet is my flow divided by my area. The flow rate will be the same. What's going to change is my speed. So this is actually equal to 0.00187 divided by pi 0.0152 squared. Okay, this is feet cube over second. This is feet squared. And this gives you a value of 10.4 feet second. So now what I can do is I can go ahead and I can replace all the values. And this is approximately equal to 10.4 squared minus 1.95 squared divided by 2 times 0.325 feet. Remember, I'm using the feet, but I'm working with feet, not inches. This is the equation I'm using, by the way. And so if you do the math here, you find this is equal to 160 feet per second squared. This is the acceleration of the problem. And note that you're talking about, this is almost, just a very interesting fact, your acceleration gives you roughly 160 feet per second squared. This is almost 5 times the acceleration of gravity. So it just tells you, it clearly tells you, even if it's a steady flow, it is accelerating as is moving along your axis, and it's moving it's accelerating really fast. So this is an example number 2 on how to use some of the equations that we derived in class.